Hi, and welcome in this new video where I'm going to keep talking about GFAS. Specifically, this video follows the three released in the previous days where I introduced the software and showed you how to perform a stage's construction analysis. In case you are interested, you can watch it from the link reported in the description down below. However, to not lose any of our most recent videos, I remind you to join our YouTube channel to be always notified. In this second video, I will show you how to perform a seepage analysis. Specifically, we will analyze the problem shown in this figure, which refers to a river bank with a reservoir level upstream characterized by a height of 2.9 meters. The river bank has a function of hydraulic retaining and, therefore, the hydraulic head downstream has to be lower than upstream, in particular coincident with the elevation of the points A and B indicated in this figure. For time reason, I will avoid repeating the procedures already shown in the previous video to focus on the aspects of the software concerning the seepage analysis. To this end, as I have already showed you how to define the geometry, generate the mesh, and assign the materials and boundary conditions, in this tutorial we are going to start from a condition in which the mesh has already been generated and material and boundary conditions have been already assigned, as you can notice from this window. However, by opening the material properties from the specific command, I would like to point out that in the panel concerning the hydraulic properties, it's necessary to assign the value of the soil permeability as well, for the soil layers of interest for this application. In this case, the permeability has been assigned equal in any direction because the material is isotropic, but it's obviously possible to account for the eventual anisotropy of the material. Let's click on OK to close the window and go ahead. To model the problem under consideration, it's necessary to assign the proper hydraulic boundary conditions to the model. To better understand, let's go back to the picture showing the scheme of our problem. Specifically, from this point to this other point, the hydraulic head has to be equal to the soil elevation plus the reservoir level, that is 2.9 meters, for a total value of 5.4 meters. On the contrary, downstream, along the line AB and on this other line, the hydraulic head has to be equal to the elevation of the line AB, that is equal to 3.5 meters. In the remaining part of the model, the hydraulic head will be variable and calculated by the software. Let's see how to do it. Let's start from upstream. We can right-click, then select polyline, and we have to select the nodes where we have to assign the hydraulic head. To exit the selection, just right-click. Then let's click on the Supports button and in the open window, let's select the panel Hydraulic. In this case, we have to assign a total head value equal to 5.4 meters in this field. In the bottom part of the window, we have to pay attention in properly selecting the start and end stages as shown in the previous video. In this case, we have just one stage, therefore the value 1 should be assigned to both. Then let's click on OK. We note that the desired value of the hydraulic head has been added to the model. Let's proceed analogously downstream. Right-click, then select Polyline and select the nodes of interest. Therefore, again from the Supports button, in the hydraulic panel, let's assign a value of the total head equal to 3.5 meters and let's click on OK. Finally, again from Polyline, let's select the remaining nodes. Then, let's open again the supports window, hydraulic, and assign for these nodes a variable total head. Let's click on OK to close the window. We notice at this point that a different value has been assigned to any of the nodes. At this point, we are ready to proceed with the calculation. From the specific panel, let's select the groundwater analysis and the seepage analysis to open this window. Concerning the unit weight of the pore fluid, being water, we can keep the default value. We can keep the default value also in the second field, which refers to a numerical control parameter. In the compute box, let's select the option free surface seepage, as we want to perform a seepage analysis. These two options define instead the settings of permeability above the phreatic surface. In case of nonlinear air elements, soil permeability is set to a very low value for the elements above the phreatic surface and the concerning nodes. In the case of true air elements, the permeability is set to 0 to these elements and nodes. In this case, let's choose nonlinear air elements. Finally, in the last cell, we have to specify the number of iterations. Generally, we can assume the default value. Let's click on OK, then Start, and wait some seconds. At this point, the analysis has finished and we can visualize the results. From the panel results, let's click on Results Plot. Referring to this problem, the outputs with the greatest interest are in the voice flows. For example, we can represent the total head from this button or the pore pressure from this other button. From this button, we can open the View Property window, from where we can select ISO lines and zero level value. Let's click on OK and again on the pore pressure button. The line shown represents the phreatic surface. Finally, let's click again on this button and change the scale factor, setting it for example to 10,000. Let's click on OK and plot velocity vectors. The scale factor has been amplified just to graphically increase the size of the vectors, as the calculated velocities are very low. Such vectors allows the users defining the flow lines consequent to the seepage occurring due to the difference in the hydraulic head between upstream and downstream. At this point, I have also shown you how to perform a final element analysis of the seepage using GFAS. Waiting to see you in the next video, I remind you to push the like button for this one. Bye!